Assalamualaikum to one and all. In today's episode, we revisit simple harmonic motion. We analyze a given displacement time graph of a harmonic oscillator and compute some of its characteristics such as period of oscillation and the like. So stick around, watch and learn. The problem is a 2.4 kilogram ball is attached to an unknown spring and allowed to oscillate. Figure 1 shows a graph of the ball's position x as a function of time t. What are the oscillations? A. Period. Letter B. Frequency. Letter C. Angular frequency. And letter D. Amplitude. And question letter E. What is the force constant of the spring? We are assuming here that the harmonic oscillator in this situation is a ball with a mass m of 2.4 kilograms. It is attached to an unknown spring and allowed to oscillate along a frictionless horizontal surface. The corresponding displacement time graph is as shown in figure 1. And our target variables are, in part A, the period capital T, or period of oscillation. In part B, the frequency small f. In part C, the angular frequency omega. And in part D, the amplitude capital A. And of course, in part E, we are to determine the force constant of the spring, denoted by small letter k. As shown in the graph, at time equals 0, the ball is at the equilibrium position, or at x equals 0. It is displaced positively at x equals positive 3.0 centimeters. Moves back to the equilibrium position at exactly t, or time equals 0.5 seconds, and then is displaced negatively at x equals negative 3.0 centimeters. Then passes the equilibrium position at time equals 1.0 seconds. Therefore, we say that the period of oscillation, right, capital T, is equal to 1.0 seconds. For question letter B, what is the frequency of oscillation? So by definition, when you say frequency, it is simply the reciprocal of the period of oscillation, 1 over capital T, or 1 over 1.0 seconds, which of course is equal to 1.0 per second, or 1.0 hertz. Part C, we are asked to find the what we call angular frequency, denoted by the Greek letter omega. So angular frequency is just equal to uh, the frequency small letter f multiplied by 2 pi, or that is 2 pi multiplied by the frequency small letter f equal to 1.0 per second. So the angular frequency omega equals 6.3 radian per second, rounded to two significant figures. And moving on to question in part D, where we asked to determine the amplitude, capital A, right, of the oscillation. So by definition, amplitude is just the maximum transversal displacement from the equilibrium position, right? It's either the maximum positive displacement or the maximum negative displacement, but we are only interested on the magnitude of the positive or the negative displacement. Therefore, the amplitude of oscillation is equal to 3.0 centimeters. Lastly, in part E, we find the force constant, small letter k, of the spring, right? Where we also assume that the spring here is an ideal spring, which means that we disregard its mass. And computing for this force constant k, we base our solution from the equation that relates the angular frequency omega with this force constant k and the mass of the ball, right? That is omega, or 2 pi times f, is equal to the square root of k over m. So that when we isolate small letter k, we come up with its working formula, right? So the force constant, small letter k, is just equal to 4 times the mass of the oscillator or the ball times the square of the value of pi, and multiplied also by the square of the frequency small letter f. That is, the force constant k equals 4 times 2.4 kilogram multiplied by pi squared, and multiplied also by the square of the frequency, 1.0 per second. So when you do our math, we arrive at the value of the force constant of the spring, k equals 95 kilogram per second squared, or the unit can also be in Newton per meter. So our answer here is also rounded to two significant figures. So that concludes our lesson for this topic. Mabuhay till the next episode. MashaAllah. Thank you very much for your indulgence. Please don't forget to subscribe to my YouTube channel, Alhamdulillah.